So we've practiced with the power rule when we're integrating. And just as a quick reminder, if we start with something that looks like this, then to integrate that, we add 1 to the exponent and divide by that same exponent and add a constant of integration. We've got that down pretty well. And so then we do one like this. We add 1 to the exponent, and I get this. It means we've got a problem because we can't divide by 0. So you ask yourself, what's the solution to this sort of problem? And the answer is the natural logarithm function. If you think back when we talked about the first and second fundamental theorems of calculus, we used the second fundamental theorem to define a function sort of like what's down here in the definition of the natural log function. In other words, f of x went from 1 up to x, which was kind of weird. And we call that an accumulation function because as x goes from 1 to whatever value on the x-axis that it ends up at, then it's accumulating area under the curve. Keep in mind, this function is just by definition. It doesn't come from algebra, it doesn't come from trig, it's just a definition, which opens up a whole new group of functions called logarithmic functions. We'll see more of those. Before we go any further, let's just take a quick look at some of the properties of the natural logarithm function. The domain is in the open interval from 0 to positive infinity, and the range goes from negative infinity to positive infinity. We're talking about a continuous increasing one-to-one function, which means it's got an inverse, and the graph is concave downward. Let's take a look at the graph. We see the y-axis is a vertical asymptote, the range from negative infinity to positive infinity, and notice something, that the graph crosses the x-axis at 1. And there's a reason for this. Any logarithm function, not just the natural log function, but any logarithmic function will always cross the x-axis at 1. And we'll talk about the reason here in just a minute. And from way back in your math education, maybe algebra, definitely about algebra 2, and pre-cal was a review of these properties. We know that the natural log of 1 is 0. We know that, looking at number 2 there, if I want to get the natural log of a product, I can just add the individual logs of the values that make up that product. And looking down at 4, we know if we want the natural log of a division problem, a quotient, then I can just subtract the log of the denominator from that of the numerator. And then going back to 3, if I want to take the log of some base raised to a power, I can move that power out in front of the log and just end up with that power times the log of the base. Again, that's a quick review. You all already know those things. On this page, I highlighted the warning that when you're rewriting logarithmic functions, make sure you check to see if the domain of the rewritten function is the same as that of the original. Always something to check. In the third paragraph, we're seeing common logs have a base of 10, and therefore the log base 10 of 10 equals 1. Now, I mentioned that earlier. So you're always going to have to ask yourself, well, what's the base? And if I've got something like this, log of 10 equals 1, what does that really mean? It means you take the base, raise it to the 1 power, and that gives you the result. If I had base 2 logarithms, the log base 2 of 2 equals 1. So I'm going to raise 2 to the first power, and I get 2. And that's why earlier I said all logarithmic functions will cross the x-axis at 1. Now, I haven't mentioned the base of natural logarithms. I have said that any logarithmic function will cross the x-axis where x is 1. Well, how's that going to work with natural logarithms? By definition. So by definition, this value e is the positive real number, so that when you integrate from 1 to e, you just get 1. Now e is an approximation you can see up there. It's sort of like pi. It goes on forever and never repeats. E's a lot of other things too, but for our purposes right now, that's the important one. All right, here's the graph of the natural log function again. We already pointed out that it crosses the x-axis at 1, but go out to where x is equal to e, which is at roughly 2.71828. Look what the y value is, 1. And that ties into something we already talked about. If I said the log base 10 of 10 is 1, the log base 2 of 2 is 1. So you could think of e as the base for natural logs. So the natural log of e is 1. So what is the derivative of a natural log function? This is kind of strange. Number 1 tells us the derivative of a natural log is 1 over x, as long as x is greater than 0. And that gets back to the domain of a natural log function. Looking at number 2, it's saying if we have some function u, and we know that u is probably going to be a substitution, then we can use the chain rule to say that the derivative of the natural log of u is just whatever u prime is over u. Let's practice a little bit. Looking at a, I want the derivative of the natural log of 2x, not x, but 2x. So I've got to apply the chain rule. If u is 2x, then du is 2. I put it in this form. And then I go back and I resubstitute what u stood for. But now then I can cancel out some of the numerator and denominator and just get 1 over x. Going on to b, I want the derivative of the natural log of x squared plus 1. Well, another chain rule situation. So if u is x squared plus 1, then du is 2x. Again, this form. All right, looking at c, I've got the derivative of x times the natural log of x. So we've got the product rule. So I multiply x times the derivative of the natural log, which is 1 over x, plus the natural log of x times 1. Just leaves me this. I can cancel the x in the numerator and the denominator, which is going to give me 1 plus the natural log of x for my derivative. Looking at d, another chain rule. I'm going to let u stand for the natural log of x, which means du is just 1 over x. Now think about that. If u is the natural log of x, the derivative of that is 1 over x. All right, we're good so far. Now what? I apply the product rule. And just kind of change the form a little bit there. Looking at number 2, I know I could use the quotient rule to get the derivative of this, but let's try what's called logarithmic differentiation. It's going to be an adventure, I promise. So the first thing I do is I take the natural log of both sides. On the right, I've got the natural log of a division problem. I know from my log rules that I can subtract the natural log of the denominator from the natural log of the numerator. I also know from those rules that I can bring that 2 exponent out front. That's what I did on the first term there. And I can do the same thing with the half on the second term. So far, so good. Now I can take the derivative of both sides. So on the left, I'm taking the derivative of the natural log of y. And on the right, I'm going to take the derivative of all the stuff that we've got written so far. On the second term inside the brackets here, I'm going to say, let's let u be x squared plus 1, which makes the derivative of u 2x. On the left, I'm taking the derivative of the natural log of y, which is just y prime, whatever y is as a function of x, divided by y. On the right-hand side, I'm taking the first term inside the brackets, so 2 times the natural log of x minus 2, the derivative of that is 2 times 1 divided by x minus 2. Second term in there gives me this. I know du is 2x, so that's why it's over the x squared plus 1 in the denominator. I can cross out my 2's, which gives me this. And you go, well, that doesn't look bad right there. And no, it doesn't, but we're not quite done because I'm looking back on the left-hand side and I've got y prime divided by y. We need to do something about that because we're really after y prime. So I just erased what we had and rewrote this where we stopped. So I've got to multiply both sides by y. Now on the left, I've got y prime, which is what I really wanted. On the right, I've got y times our values in the brackets. But what was y? Oh yeah, this. So I've got to multiply that times the values in the brackets. And I'm getting this little nightmare. Okay, when some of the smoke clears, this is what I've got so far. Now I'm looking at the numerators and I'm saying, well, we got something common there. In the denominators, we got something common. So when I multiply everything out and collect like terms, this is what I end up with. Now, yeah, this worked. I think if you use the quotient rule, you'd get the same thing, I hope. So just wanted to introduce you to this concept of logarithmic differentiation. Now, I took this value right here and worked it out further. Could you have stopped right here and had the right answer? Well, yeah, technically. Maybe I didn't need to go through all of that to get a final answer like I did up there in red. Could I have stopped right here? Sure. It just depends on what the problem is asking, how well refined do you want the answer to be, and so forth. But all three of those are the right answer. The one in red up there is just the reduced version, if you will. Okay, a lot of times when we're doing natural logs, we're going to be using absolute values because the natural log function is not defined for negative values. And looking at theorem 5.4, it shows us that if I take the natural log of an absolute value of a function and find the derivative, it's just u prime over u, which is what it was before we put the absolute value symbols there. So natural log pretty much ignores that absolute value. Let's put this into practice a little bit. Part A says find the derivative when f of x equals the natural log of x minus 3. Okay, I'm going to let u be x minus 3, and du is just going to be 1. So the derivative is just going to be 1 over x minus 3. Notice it's not 1 over the absolute value of x minus 3, which is the point I'm trying to make here. Looking at b, I've got f of x equals the natural log of cosine x. Chain rule time, so I'm going to let u be cosine x, which makes du negative sine x. Well, just following the form, I know the derivative is going to be this. But then my trig brain kicks into gear and goes, well, yeah, that's an okay answer, but I could also rewrite it like this. Now, a little bit of foreshadowing here. If we were going to integrate tan x, what do you think that would lead us back to?